In this video, we will talk about how to estimate the marginal cost using the derivative. So let's begin by doing a review of marginal cost. So let's suppose that we have the cost function c of x equals 13x plus 25. And the units of cost here, I'm going to say, are dollars. Remember that marginal cost is the cost of one more item. So if we want to find the marginal cost, there are a couple ways that we can look at it. We have a shortcut for a linear function, which involves looking at the slope, but I want to talk briefly about why that is. Why does that work? So I'm going to make a table of values where I keep track of x and c of x. So keep track of the number of items and the cost of selling that number of items. So if x is 0 and I plug that in, I get 25. If x is 1, then I get 13 plus 25, which is 38. If x is 2, I'll get 26 plus 25, which is 51. And if I keep going, if I plug in 3, we'll get 64. So marginal cost is about, if I look at one of these cost values and I increase the number of units by 1, how much did my cost change? So from 25 to 38, the cost went up by 13. And from 38 to 51, well, it went up by 13 again. And from 51 to 64, it also went up by 13. So in this example, the marginal cost is constant. And it's constant since the function is linear. So this function, it has the form of the equation of a line. So the marginal cost here, regardless of how many items we already have sold, the marginal cost of one extra one is $13. And when my function is linear, the marginal cost is the same thing as the slope of the linear function. Because the slope here represents how much does the cost change when we increase the number of units by 1. And that's precisely what marginal cost is when we're talking about a linear function. Alright, so what if my function is not linear? What if I have something like x squared plus 2x, and that's my cost function? Well, I can't just read off the slope because this isn't a linear function. Instead, what I can do is I can make a table of values, so keep track of x and c of x. And I'll do 0, 1, 2, and 3 again. Plugging 0 into this, we get 0 squared plus 2 times 0, which is 0. Plugging 1 into it, we get 1 squared plus 2 times 1, and that's going to be 3. And I'm going to quickly do these others. If I plug 2 into it, we'll get 8. If I plug 3 into it, we will get 15. So now, if I look at the marginal costs, so if I go from this initial cost of 0 items up to the cost of 1 item, that went up by 3. And then from 3 to 8, it went up by 5. And from 8 to 15, it goes up by 7. So the marginal cost here is not constant. The marginal cost, we have to specify based off of how many items we've already sold. So the marginal cost of just the first item, so the first item on its own, which means if we're starting at 0 items and then we go up to having 1 total item, that marginal cost is $3. But for the second item, so that means we already have sold 1 item, and the cost of that was $3 total to the store, or whoever the seller is. Their cost is $3. From selling 1 more item, that extra cost is $5, and that's the marginal cost. So when my function is not linear, like number 2 is, this function, x squared plus 2x, we can use this idea to get the marginal cost. So now the question is, how do we find the marginal cost for functions that can't be evaluated without a calculator? So what if I want to do this and I have a function like square root of x that I can't plug in values into without a calculator. Or sometimes I want to be able to do stuff like this without even having a formula for my function. How could I get the marginal cost? And the answer to that is we will use tangent lines. When we talk about tangent lines, we were talking about the derivative. So we'll use tangent lines, aka derivatives, because those are connected to tangent lines, to estimate it. So we will estimate our marginal cost using derivatives, using tangent lines. Let's look at an example. Let c of x be equal to 40 times square root of x be the monthly cost of selling x hats for a hat store in dollars. Part A is, what is the approximate cost of the 17th hat? Okay, so when we talk about the 17th hat and its cost, we're talking about the cost to the store. So we're not asking how much is the store charging its customers for the 17th hat. So there's some cost of selling hats that the store has, and we're asking what is the approximate cost of the 17th hat to the store. Okay, so if we're trying to find the cost of the 17th hat just on its own, that's equal to the total cost of 17 hats minus the total cost of 16 hats. In other words, we got to find the total cost of selling 17 hats and subtract the total cost of selling 16 hats, and that would give us the cost of the 17th hat alone. Okay, so in terms of our function, the total cost of 17 hats, well, that's c of 17, minus total cost of 16 hats, that's c of 16. And plugging into this, we get 40 root 17 minus 40 root 16. So the question I want to ask and then try to answer is, can we approximate this without a calculator? That's going to be our goal here. And the answer to that is yes, we can. And the idea is going to be to use tangent lines. So yes, we can, and we're going to use tangent lines to our function to approximate this. All right, so I'm going to draw a picture. So in my picture, let's draw some axes. Whoops. So let's draw some axes. I'm going to draw a vertical y-axis and a horizontal x-axis. And then I'm going to draw the graph 40 times square root of x. So 40 times square root of x, it looks like the square root of x graph, but the 40, having the 40 in front, is going to stretch the graph vertically by a factor of 40. So overall, it'll still have the same shape that the square root of x graph has. It's just stretched vertically. Okay, so what I'm going to do now is I'm going to put a tick mark where x is 16. So put a tick mark where x is 16. Let me label that a bit better. And at that point on the graph, that's somewhere here. So the y value here is c of 16. And c of 16 is something that we know. If we wanted to figure out what c of 16 is 40 times square root of 16, we could work out what that is. C of 16 is 40 times 4, which is 160. So c of 16 is a nice known value. But we want to know what the difference is between what's happening at 16 and what's happening at 17. So I'm going to draw my graph not to scale, just so I can draw the picture a little bit bigger, not so that it's not super cramped. Okay, so at 17, the point on the graph is here, and this y value is c of 17, and that's the one that we're sort of unsure of what it is without a calculator. So in terms of this picture, if I draw a horizontal line here from where 16 is to where 17 is, and then a vertical line that way, what we want to know is what this vertical distance is. Okay, so I'm going to call this the exact change in C, which is C of 17 minus C of 16. Okay, so we want a way to approximate this vertical distance, and we'll do that by drawing a tangent line. So we know what's going on with our function at 16, because 16 is a nice value to plug into the function. So 16 is a nice, I'll put that in quotes, nice value for our function. Meaning I can plug 16 into the function, into the square root function, and I know what I get out. So I'm going to draw the tangent line at that nice value. Okay. So here's my tangent line. So I'm going to call this tangent line L. So L for line. So what we'll do is I'm going to plug in 17 into the equation of the tangent line, and that's going to give me a y value up here on the tangent line graph. And then I'm going to instead find the vertical distance from this point on the tangent line graph to the bottom of these tick marks here. And I'm going to call this vertical distance change in L. Okay, so this is going to be equal to L of 17. So that's this point on the tangent line graph when we plugged in 17, minus L of 16. So L of 17 is up here on the tangent line graph. L of 16 is down here. Notice that L of 16 is the same thing as C of 16, because the graph, the curve, and the tangent line have the same y value when x is 16. That's why L of 16 and C of 16 are the same. But L of 17 and C of 17 are different. Okay. So we are going to try to find this change in L, because the change in L is going to be approximately equal to the change in C. Okay, so how are we going to do that? How are we going to find the change in L? So the change in L is this vertical distance. And if you divide that by the change in x, and the change in x is this distance right here, that's the change in x, that's equal to the slope of the tangent line. And this equation, this slope equation, is going to be the key idea for how we find delta L, the change in L. Okay, so let's summarize the idea here. So we are going to find, the slope of the tangent line. Let me give myself more room here. Find the slope of the tangent line, which I'll call L of x, using the derivative. So the derivative is what we can use to find the slope of the tangent line. And then after we use that, we can use this equation that the slope equals delta L over delta x to get delta L. And this is going to be our approximation. Our approximation to delta C. All right, so let's do that. Let's begin by doing step one. Let's get the slope. Let's get the slope of the tangent line. All right, so we do that with the derivative. So our function c of x was 40 times square root of x. And to take the derivative of that, let's write square root of x as x to the 1/2 as a power. So now I can use the power rule to take the derivative. And the power, the 1/2 comes down, and it'll multiply the 40, and I'll get 20 in front. 20 times x to the, and then I subtract 1 from this exponent. So 1/2 minus 1 is negative 1/2. Okay, if it's not quite clear how I got that derivative, review section 4.1 in our videos on derivative rules. I'm using the power rule to get this derivative. Okay, and if I rewrite this, this is 20 divided by square root of x on the bottom. Because negative power means bring it to the denominator, and on the denominator, this would be 20 over x to the positive 1/2, and x to the positive 1/2 is the square root of x. All right, so now we're ready to write down our slope of the tangent line at x equals 16. We were taking the tangent line to the curve at x equals 16. Well, that's going to be c prime of 16 And plugging in 16, we get 20 divided by square root of 16. So 20 divided by 4, which is 5. So using this equation here, the slope of the tangent line is supposed to be equal to rise over run. It's supposed to be equal to the change in L, because I have L as my variable instead of Y, over the change in X. All right. So this means that 5 equals change in L is an unknown. But the change in X in my picture, how much was X changing? It was from 16 to 17, so the change in X is 1. The run is 1. So that's the change in X here. The change in X is just 1. In fact, let me mark that in my picture. The change in X in this picture actually just equaled 1. All right. So this just means that delta L is 5. Okay. I need a little bit more room, so I'm going to scooch this down. All right, so I scooted that down. So now we are ready to write down our answer. Thus, the approximate cost of the 17th hat is delta L, what we just got for it. It's $5 approximately. Okay, that's approximately how much that 17th hat costs the store. All right, so there's a couple things I want to note about this. So the first is, well, how good of an approximation was this? So let's compare this to what the exact change in cost was. So the exact change in cost is C of 17 minus C of 16. And C of 17 is 40 times square root of 17. C of 16 is 40 times square root of 16. So if we use a calculator to approximate what this is, to 5 decimal places, it's 4.92423. And the units are dollars. Okay, so, and I did this with a calculator. So with a calculator. So this is pretty close. So what we got using our tangent line is pretty close to the exact value using a calculator. Okay. So if we have calculators though, why don't we just use them to figure out stuff like this? Like, why bother with tangent lines and approximating? And the reason behind that is we don't always have formulas for functions in the real world. So specifically with business and econ models, we often don't have a formula for functions that we're looking at. So functions for things like revenue and cost and profit in the real world may not just depend on one variable, they might depend on many variables. And that's something that you'll look at in Math 31, functions of more than one variable. So when you don't actually have formulas for your functions, you just have data points, like historical data. And often, then we use those data points to make projections into the future. So we're going to project and sort of estimate what's happening in the future using data points for our function. And in this scenario, we can't get the exact value of delta C, or whatever our function is, if it's not a cost function, but we can approximate it. So we could approximate the instantaneous rate of change. That's the slope of the tangent line. You could approximate the instantaneous rate of change using an average rate of change. And that's where the data points come into play. And that's one of the main reasons why we care about this, why we care about approximating marginal cost and other marginal things. Because we won't always have formulas for our functions. And in that case, we can use this idea of approximations to make projections into the future. All right, so next we're ready for a definition. So we've seen that there's a connection between C prime, the derivative, and estimating the marginal cost. So because of that, C prime of x is called the marginal cost function. So it represents the approximate cost, the approximate marginal cost, approximate cost of one more item after the xth item. Okay, so when we say marginal cost function, we actually mean approximate marginal cost function, because the derivative will approximate the marginal cost. All right, so let's do another part of this example. What is the approximate cost of the 26th hat? So 26th hat, if we're talking about the cost of the 26th hat alone, this means that 25 hats were already sold. Okay, so there's already 25 hats sort of sold, and we just want now the approximate cost of one more. So to do this, we want C prime of 25, not C prime of 26. That's really important. Not C prime of 26. That's a really common error that we see with this marginal cost function. Because C prime of 25 means, well, there's already 25 hats done. That's what the 25 means, plugging that in. Whoops, I forgot to write the vertical line of the word the here. Okay, so I just wrote that in right now. Whoops, erased it again. Okay, so C prime of 25 means we already have 25 hats. And now tell me the approximate cost of one more. In other words, the 26th. Okay, so if I use my derivative, so let's recall C prime of x was 40 over square root of x. And if I plug 25 into that, we will get 40 over root 25. Oh, sorry, I think I miswrote this. I think this should be 20. 20 on the numerator. 20 on the numerator. Okay, so this is 20 divided by 5, which is 4. And the units are dollars. Okay. So having the derivative function gives me a really quick way to approximate the cost of one more item. Okay, so now let's do another part of this example. What if we wanted the approximate cost of the 26th and 27th hats combined? So not just one extra hat, the 26th, but the 26th and the 27th. So it's hard to estimate the 27th hat using C prime of 26, since square root of 26 requires a calculator. The whole purpose of this problem is to approximate the square root function. So if we have to evaluate the square root of some number using a calculator, that's kind of defeating the purpose. So how do we get around this? So the way we're going to get around this is I'm going to draw a picture. So I'm going to draw a picture of my axes. Okay, and then I'm going to draw my function. So I'm going to draw this square root function. It's curving upwards like this. And I'm going to draw a point at 25. So at 25, and I'll draw a point there. Actually, let me draw this curve a little bit better. Let me make it curve a little bit more. Should curve a little bit more smoothly. It should be a little bit more like this. Okay, and then I'm going to draw a tick mark at 27. So I'm going to use 25 as a reference point because this is, the 25 is a nice value. And when we draw the tangent line, we want to take the tangent line at a nice value. And by nice, I mean something that's easy to plug into my function without a calculator. Something I can work out by hand. Alright, so now if I draw my tangent line at that nice value, we get something like this. So our tangent line at 25. So right at 27, if I plug 27 into my function, we get a point here. And if I draw my horizontal dashed line from 25 to 27, and then a vertical line, we want to know this vertical distance. That is delta C. But we can approximate that using, if I plug 27 into my tangent line, I get a point up here. So we can instead find this vertical distance, which is delta L. So we'll find that vertical distance. All right, so we can do that by using the fact that the slope of the tangent line is equal to the rise, delta L, over the run, which is delta X. Delta X is now going to be this horizontal distance. So to get the slope of the tangent line, we need C prime of 25, because we're taking the derivative at 25. Or sorry, we're taking the tangent line at x equals 25. So this equals delta L on top. Delta X in this problem is 2. Now my run is 2. C prime of 25 we already found. If I zoom out a little bit, what was C prime of 25? We got in part B that C prime of 25 was 4. So 4 equals delta L over 2. And if we isolate delta L, we get that it's 8. And that is the approximate cost of the 26th and 27th hats combined. So it's because it's a cost, it has units, which in this case are dollars. And that is my answer right there. All right, in terms of our goals, we have done our first 2 goals. We've reviewed marginal cost from sections 1.2 and 1.3 at the beginning of this video. And then we used those ideas to talk about how we can estimate the marginal cost using the derivative. And we introduced what's called this marginal cost function. So it turns out we can use that same idea of using the derivative and using tangent lines if we want to estimate the marginal revenue or estimate the marginal profit. And I'll begin my next video by talking about that briefly, but I'll spend most of the video talking about how we can use the derivative to determine when things like cost, revenue, or profit, when our functions are increasing and when they're decreasing using the derivative.